Hello, everyone. I have the pleasure of introducing you Mr. Antonio Cuni. He's the principal engineer at Anaconda. Let's welcome him with a big applause.
Hello, thank you everyone. So we are here to talk about Spy static Python. I tried to find like a short summary of what it is, but I couldn't. Like the shortest thing that explains what is Spy in detail is like 30 minutes talk. So let's just start with it. I feel it's best is to start thinking about Spy as like a thought experiment. So we have Python. We would like it to be fast. We want to compile it. Um, there are other projects which try to compile Python to remove features to make it easier to compile, but usually you end up with a language which is not as nice as the Python that we know and we like. So the question is how much of the features of Python we can remove so that it's easy to compile faster and it still feels like the language that we like. So this is the kind of the basic goal that I want to get. And the other like angle of viewing of this is if I show you this piece of code, I mean everybody understands what it does. Like it's obvious. We import NumPy, we have a constant, then there is this function which does calculations, takes two floats, an array, blah blah blah. And the problem is that as humans, that's obvious what it does. But if you're a compiler, and you want to compile this code, then you have troubles. Because all of basically every single line of this code could lie. Lie in the sense that it could not do what you think it does. No, the module NumPy could not be NumPy. It could be something else because I did something strange with the serial modules or a custom importer. The n could change. The type annotation could lie because who knows? And so if you have a compiler, they have a very hard time to produce efficient code for this. And I think it's very strange because, like, as humans, we know, and nobody would ever pass a code review if this code does something different. But a compiler cannot use this information. So let's try to do better, basically. I claim that in practice we already use a subset of Python, the one that we use for real, because there are tons of stuff which are in theory possible, but you don't do it. Like you can modify the dunder class of an instance at runtime. Who does it? Well, I did in the past, but I mean, you can do tons of strange stuff. And moreover, now in the latest years, we have this huge community that wants static typing. They want it for like have better safety. But the way static typing is done in Python, it was like put on top of the existing features, so it was not like designed. It's not a language designed for static typing. So you have a strange situation in which you have these annotations, but they are not really safe in the sense that they can prove something, but your program can still do something different because there are a lot of ways to escape it, and it doesn't help at all with performance. So the idea is, again, let's design the language from the ground with the type system with the idea that, okay, let's make it safe and fast. And I'm fully aware that there are tons of other projects like this. There are a lot of quasi-Python languages, subsets of Python, variants, number, Python, Cython. PyTorch has a JIT, which doesn't support all the features. And like, we are exactly in the situation of XKCD. I just want another one which is better, of course. Yes, sure. I think that the biggest difference of my idea for Spy compared to all the other examples that I'm giving here is that usually this subset of Python or compilable Python focus on the inner loop, let's say. So you have a function and you do numerical computation fast, or they restrict, like you have like classes, but you cannot do decorators, or beta classes, and things like this. So Spy wants to focus more on the other side of the story. So I want a system in which we can use the nice features that we all like in Python, but then you also can do the last mile optimization, like let's call them. So goals. I want a language which is easy to understand, and it's Pythonic. So like, if you look at it, you just think you're writing normal Python code, and you don't even kind of notice the differences. I want it to be easy to implement, because there are attempts to make Python, like the full Python, fast. I've been working for 20 years on PyPy. The C Python people are doing a JIT. There is Cinder. I see some Cinder people in the room. Like, there are attempts, but usually you need to have to put a lot of complexity into the implementation, and it comes with drawbacks. So again, I want a language which is easy to implement, and since it's easy, since the semantics is designed in such a way to be fast, you kind of have steady performance. Like, in any JIT compiler, you arrive at a point in which, if you write the code carefully enough, then you have super performance. Then you change a comma in a completely unrelated file, and then you don't know. Like, you are 20% slower, 2 times slower. I've seen these things in practice. And also, I don't want people to be chasing the optimizer, because if you want to use PyPy, or again the CPython JIT when it will be there, you need to have a very good knowledge of the internals in order to use it to the fullest. And if you don't know, then yeah, maybe it's faster, maybe it's not. You don't really understand. The non-goal is to be 100% compatible with Python, the existing CPython. I don't think it's possible, basically, to achieve all the goals that I want without, well, removing some stuff. And again, a very high-level view of what I want to achieve. Imagine to have, on the left, a high-level language, like Python, which is interpreted. So we have these blue nodes which are interpreted, and they do a lot of stuff. And to do the same computation, you can use a different lower-level language, like C, or Rust, or whatever, which is compiled usually, and so you generate executable. And you see that on the right, our graph has less nodes, and this wants to represent the fact that usually in a lower-level language, you do less stuff at runtime somehow. For example, if you have A plus B in Python, well, you do a lot of stuff. You need to do a lookup of methods, understand their type, and etc. In C, well, the compiler can just emit an instruction. So this is the big dichotomy. The idea of Spy is to have a language in which we have a lot of compilable, a lot of the logic of the program can be compiled easily. There is some logic of the program which is, for example, operator dispatch, like as complex as in Python, but we can optimize it away, for example, using an interpreter. So in Spy, we will see it better later, but in this example, you have part of the programs which can be evaluated in advance somehow, so you can remove them in a process which I call Redshift, because I remove the blue nodes and I just remain with the red ones. And so I start with a program with complex semantics. I evaluate ahead of time all the strange stuff, let's call it, and then I get something which is compilable. So this is the super high level idea, but then we'll see in details what it means. So what are the modifications to the semantics that we need to do? The first is that I want to formalize something which actually already happens in Python, which is that usually you have a lot of logic at what I call import time. So when you import a module, a package, a set of modules, you have a lot of stuff happening. You have decorators, you have meta classes, you have module level logic going on. You do pre-computation of something. And then, usually, you don't modify these things. Like, maybe you do a lot of monkey patching on classes. There are like SQL Alchemy does incredible stuff at this time. Flask, Fast API, they all do a lot of logic. But after the program is initialized, then the word is fixed. So I basically formalize this, and I say that after this, well, the word is frozen, and you can no longer modify things. And then type annotation are actually enforced. So in Spy, if you have a type annotation and like a variable, and you annotate with a type, and you assign a value which is not compatible, you get a type error. And you will think, yeah, okay, but then you do more work, not less. But we will see later why this helps. And finally, whenever you do an operation like a plus, but operation can be something like a get out, like a dot, or a square bracket. What happens now in Python is that you do a lot of work to locate the actual logic that you want to execute, and then you do a bit of work, which is the actual logic. And basically, I split, like formally split this logic into two steps. One which is, well, let's locate what is the logic that we want to execute, and it will be a blue node in the graph before, so it will be optimized away, and then the actual logic at runtime. And again, we will see it later. So, execution phases, as what I was saying now. You have import time, you have a freeze, and then you have the normal runtime. At import time, we statically resolve all the imports. This is a big difference with what Python does, because in Python, you can always import a new module, and any JIT compiler, any implementation has to take this into account. The idea is, well, let's define the rules in such a way that we know what are the actual modules, we can locate them, we can execute all the logic, and then we move on. At this stage, we have mostly normal magic Python semantics. You can do all the tricks that you want, and you can implement all the cool libraries that we like. Because again, I want to be able to implement SQL Alchemy, Fast API, and whatever. Then, in the freeze phase, all these variables, all these objects that has been created are frozen, and then it means that after this stage, if you try to modify them, then you get an error. And this includes, for example, like, again, in the Fast API case, you have probably a list of URLs that you want to dispatch to, and these become frozen. And then it's much easier later to optimize on this. Of course, there are still cases in which you want something which is mutable, but then you annotate it explicitly. So by default, you have something which will be frozen, which is, I assume, 99% of the cases. And then, if you really want, you can have something mutable. And then, yeah, runtime, what I was saying. Normal execution, as you would expect, apart the fact that types are checked actively. And then, once we have this set of rules, we can become, like, that's where the magic starts, basically. Remember, here I'm saying three phases: import, freeze, and runtime. So I have this phase, which I call 2.5, partial evaluation, which is done between the freeze and runtime. And now I'm in a situation in which I have a lot of operations on data, which I know they are immutable because I'm enforcing it. And then I can optimize them away. So if I have a global class with an attribute, and I do lookup at the attribute, and I know that the class is immutable, and the lookup is resolvable ahead of time, well, I can just take this lookup and put the actual value in the graph. And if I have the lookup of the operator, again, I have a plus, but I know the types, I know everything, I can just find the implementation, the low-level implementation that I want. If the bug is another very good case. If you have a debug global variable and you have your function with just two different things in case of debug enabled, well, I can statically know whether this branch is taken or not, and I can just remove the code which is not needed. I can enroll loops if I'm looping over, well, constant lists. And yes, basically, it's what I was describing here. I start from a graph. In this stage of the implementation, it's really an AST interpreter so far. So I start with a graph of nodes in the AST, and I can just remove some of them. And in some others, some logic is kind of mixed, half blue, half red. So I can just make a new node with less logic here, basically. And then I need basically two things for achieve my goal. I need an interpreter because it's easier to implement, it's easier to debug, it's a nice developer experience. We all like the interpretation nature in Python. We modify the file, run the test, and everything works. But I also want a compiler for speed. So you can run your program in full interpreted mode, and then it means that import time is interpreted, the partial evaluation stage is using the interpreter to evaluate these blue chunks of the graph, and then also runtime is interpreted. In compiled mode, the first two phases are still interpreted, a bit slow maybe, maybe we can speed up later, but then I get this graph, I compile it, and the runtime is super fast. Currently, for my compiler, I'm also using a very dumb approach. Like, I'm really optimizing time to market. So far, I'm alone. I don't want to spend too much time on doing unnecessary stuff. So the easiest thing to get executable code is to generate C code from AST, and then use a C compiler to get assembly code. But since I removed all the craft, all the stuff before, well, it's actually very easy to do. And yeah, this is basically what I described already, but I wanted to have a slide in case of people looking just at the slides. You have this AST with blue and red nodes, and then I have this phase which I call Redshift, which removes the blue stuff, and you get with only the red one. And now we will see examples, because so far it's a bit maybe not so clear. This is the super simple example. I have a function, normally, which calls this k, okay? And k is marked as blue. I mean, the details of the syntax might change. So far, I just have this decorator. And basically, what happens here is that the partial evaluation time, well, we just compute this value and substitute it here in this node. And this is something that any C compiler can do easily. I mean, this is not rocket science. The difference is that this is actually guaranteed by the language. It's not that I need to hope that the compiler will be able to optimize it. I know that it will do. I can show you. I think it is called bluefunc.spy. Oh, so something that I didn't say. This is not compatible with Python. And I don't want to lie to people. There are a lot of supposedly compatible with Python projects which are not, and they use the .py extension. I think this causes a lot of confusion. So for spy, I'm just using a new extension. It's opt-in. If you want to use your old Python code, well, .py. If you want to opt in and use Py features, well, you change the extension. It's very clear what's happening, basically. So I have this file, bluefunc.spy. I can run spy. Of course, I can just compile it, for example, to WebAssembly. But I have this option which just stops the compilation after the partial evaluation and then dumps the AST into readable spy code to see what's happening at this stage. So if I redshift bluefunc, I get an error. This is actually a nice typo. I think it will stay in the video, okay? Why nobody told me? Thank you. So this is what happened. So you get basically a nice dump of the graph. But this is really, like, this is not textual substitution. Like, it's really doing a lot of computation behind. But you get, like, the result automatically computed. Things becomes more interesting when you start to do, well, more interesting stuff. So, for example, closure. In this case, I have, well, this is a classical function, like textbook example of a closure. I make an adder function, and then I pass one parameter, and then the second. And then I create two of them, one to add 5 and one to add 7. Well, this is kind of normal Python. We all know what it does. But if we do it in Spy, how is called it? It's make adder. So cat make adder.spy, okay? And then I redshift it. What's happening is that all the blue code is optimized away. Look, I no longer have this blue function here. And instead of having this call, well, I actually created two instances of this function. And then when I call them, here you see that I'm also resolving the lookup ahead of time. This is a special syntax which I invented just for like being able to visualize it. Basically means that I have a global add 5 in the make adder module, and this is just it's not the lookup, like it's there. The compiler can just call it without finding it, because in Python, every time you do a global lookup, you have to find it. And then we have type checking. What do you think it happens? Again, Spy is also an interpreter, so I can run programs. So what do you think it happens if I run this program? Note, I have an inc function which takes an integer, and here I call it with an integer, and here I call it with a string. But this condition, well, this is never reached. Nobody wants to try. So let's try. This is called type error spy. It works. And you say, well, what? It should be a type error because here it is. But what's actually happening is that we redshift this code. This does basically type check. And we partially evaluate and we see, OK, this will raise a type error. And you say, OK, that's not very nice. I would like to know in advance if I have type errors in my code. And I will have two modes. This is not correctly implemented, to be honest, but the idea is to have two different modes of collecting errors, lazy and leaguer. In lazy mode, it's what I showed you. Like all the type errors, well, will be turned into raise and will be raised at runtime if you hit them. And in eager mode, well, I can just collect every time I'm partially evaluating a type check and it becomes a type error statically, then I can just report it to the user, and this is equivalent of what MyPy is doing, basically. But I can choose. And lazy errors are very useful, for example, during refactoring. You are changing the name of a method, and then you have tons of errors. You cannot even run the code until you fix everything. But with lazy errors, well, you can fix them one by one. You run the test, you see where is the failure, and fix it. So I think there are merit on both approaches, and with Spy, well, you will be able to choose, basically. And then all this partial evaluation stuff becomes interesting in case of generics. So we have a function here, and takes two arguments of type, and the type, what is it? Well, it depends on the argument here. So I can create two copies of the function using types, using different types, and what's happening is that I get two actual implementations of the function, one for A32, one for F64. And I can go further. I can use it for classes. I can have a function which returns the classes, and I pass the type, and then I have a generic class, a generic list, generic dictionary, generic container, whatever. So far, this is the syntax which I support, but the idea is to tweak a bit the syntax of Python, and probably I would like to support something like this. So this will be equivalent to the line above, but it's how you implement generics in a way which is completely consistent with everything I'm talking about. Remember when I was talking about this two level of operation dispatch? That's what's happening in Spy. So you have an operation, in this case, plus, and then in Python, this is based, the result is based on the dynamic type of the instances, of the objects. In Spy, and this is another big deviation from the language, I understand, this is determined by the static types. So basically, it's kind of equivalent to this. I have this operator called uppercase add, which is something which takes types and return a function which executes the addition. So, like again, x plus y is basically let's get the opimp for these types and then execute it. But again, these are all blue lines of code, which are optimized away by the compiler. And I can show you, for example, I have this op dispatch, and here I'm calling the uppercase add operator on different combination of types, and let's see what it does. What's happening is that in this case, the first case, well, I get a function which is specialized for adding integers. In the second case, I get a function which is specialized for strings. In the third case, I get a not implemented, because, well, it's not implemented, integer plus string. And then at runtime, if I get not implemented, I raise an error. And then this error is also, like, in eager mode, it's just reported to the user. And then, once I'm in this situation, well, implementing this function in C is super easy. So, like, the C compiler will be able to just inline it, and I get a add operation in machine code, basically. But then I can go further. getArt is the same. Like I can, when I have x.name here, actually what's happening is that I'm asking the class, the type of x, what is the operation for getting this particular string? And then, well, it can do all the logic at blue time, at import time. I can choose stuff depending on the actual string, and then returns a very efficient implementation. Another deviation from Python is that, again, everything is based on static dispatch, which means that if I have two objects of type object, well, this line is a type error because I don't know how to add two objects. But then I have a special type which is dynamic, which, well, guess what it does? Dynamic dispatch. So there are cases in which dynamic dispatch of Python is actually useful, but I claim not many of them. So it's, again, opt-in. When you need it, you can. If you don't need, you don't pay. And I'm almost out of time, but I think this is like a good example which summarizes everything which I said so far and probably can give you an understanding of how far we can go with this. Imagine I want to implement some library for accessing C-like structures. So I have a point in memory with two fields which are I32. So like really, somewhere in memory I have a pointer to these two words, well, two values. And whenever I do my point.x, I want to just load this value from the memory and put in a register. In Python, it is just not possible. You need a lot of support from the compiler. You need special cases, and etc. In Spy, I can write a library, like a user level. This could be in the standard lib, actually. And then I have this class point, which has a meta class of struct, and then x is a field. This is a type. It should be an equal. And whenever I do point.x, then, well, it does all the lookup. It does the getArt, which I showed earlier. It uses the descriptor protocol, but this time at blue time. And then you get an opimp, which is specialized for the type, which is I32 in this case, and the offset, which is 0 or 4, depending on whether it's x or y. And again, this is logic that in Python you pay at runtime. There is no way of or if you have a JIT which is very good, well, it can remove a bit of it, but not all of it. And in Spy, all of this is, well, removed. So I can show an example on the screen, but it's basically what's happening is here. So if you have then p.x, then this is basically a setat operation, and then I resolve all the stuff. I call this dunder set uppercase descriptor, and then I get a low-level implementation which knows how to do a mem move in C. And I feel this like, from the point of view of someone who writes compiler and etc., it's like magic. I can now implement low-level stuff in Python without paying performance. And I can totally imagine implementing classes in Spy using this mechanism. It's actually what I plan to do. I'm not there yet. The second example is similar, but I mean, while we are still at the time, I can just show it. A big target for Spy is WebAssembly. I started to work on it while I was in the Python team at Anaconda. And it's kind of perfect target because in the WebAssembly, size matter, so you want to ship small binaries. I want interaction with the JavaScript. I don't want to write this logic in the compiler itself. It's too hard. I can implement the logic to interact from Python to JavaScript in Spy itself and remove all the overhead. So I have, basically, I can have this kind of code, and it works. I don't have time to show it, but trust me, it works. And then you have a window, which takes a document, and etc. At low level, I need to do a set of calls which are ugly like this. JS getArt, and window, and then you pass document, and then there is JavaScript code which does not know how to deal with it. If I want to call a method, I need to, and all this stuff. but I want a high-level API. In Python, you do something like this. You have a JS ref, and then you have done the getArt. At runtime, every time you do window.document, well, you execute the getArt, and blah, blah, blah. In Spy, you do something like this. So the getArt logic is optimized, like it's partially evaluated away, and you get, for every window.document, we get basically a specific function which calls this JS getArt using a specific attribute, because this is no, not compile time. And I mean, yeah, I don't have time to show it, but like, okay, maybe I have. Let's do it. I think it's here. So if you have demo.spy, and you see, like here, document equals windows.document. If I redshift it, basically, all the nice syntax which I have in Spy, it's translated into these low-level calls, which are much efficient to implement for a compiler. I will have syntax sugar in the future, so you don't have to write this ugly two-level step. You can write it probably something like this, so you can have a function and some parameters which are blue, and so specialized to compile time, and other which are red, and then will be specialized, like will execute at runtime. Where we can go from here? Well, with Spy, you will be able to produce executable. I plan to have integration with WASM. This is actually already working, basically. We can integrate with CPython. We can, for example, produce CPython extension. This is not there yet, but I can totally imagine using it like this. Or, and this is something I was discussing yesterday with the Cinder people, I can imagine having a Spy emitting specialized bytecode, which Cinder, which is a compatible implementation of Python with a JIT compiler, can run. So kind of the best of two worlds. But we will see how it goes. Anyway, I think I'm out of time, so thank you. Oh, before I forget, I want to take a picture of the room, because there is the no-guild talk, and I thought it was much more interesting than mine. So thank you for coming. I didn't expect so many people. You can say that you were at a Spy talk when it was first presented. Yeah, sure. github.com/spylang/spy. I don't even have a README, but yeah, it will come.